Traditional AI models are often regarded as black boxes. This perception arises from the complex and dense nature of their neural networks. These networks contain numerous interconnected connections. The intricate structure makes it difficult to understand the model's decision-making process. The complexity obscures the reasoning behind the AI's outputs. Circuit sparsity is a training method for AI models. It focuses on creating sparse networks with fewer connections. This approach aims to simplify the internal workings of AI. Simplified AI models are more interpretable. The method enhances the transparency of AI decision-making processes. Neural networks can be visually represented to illustrate their connection density. A dense neural network is characterized by a high number of interconnections between nodes. Conversely, a sparse network has significantly fewer connections. The visualization highlights the structural differences in network connectivity. Sparse model training involves selectively removing connections within the neural network. The majority of connections are intentionally set to 0, creating a sparse architecture. This process drastically reduces the number of active parameters in the model. The model is compelled to distill its knowledge into a smaller set of crucial connections. This compression enhances efficiency and reduces computational demands. Sparse models can maintain comparable performance to dense models. This is achieved despite a significant reduction in the number of connections. Sparse models efficiently compress internal logic. The compression allows for similar results with fewer parameters. This highlights the effectiveness of sparse model architectures. The efficiency of sparse models is a key advantage in certain applications. Sparse models and dense models offer comparable levels of accuracy. Sparse models utilize internal thinking machinery for processing information. Dense models also rely on internal thinking machinery to perform computations. The thinking machinery within sparse models is significantly smaller in size. Specifically, sparse models' machinery is approximately 16 times smaller than that of dense models. This size difference highlights a key advantage of sparse models in terms of computational efficiency. A circuit refers to a specific configuration within a system. It comprises a small, interconnected group of internal units. These units can be neurons, attention channels, or memory slots. The circuit is defined not only by the units themselves, but also by the precise connections established between them. OpenAI employs coding challenges to evaluate sparse models. These challenges involve tasks like ensuring correct string closure with quotes. Another task assesses the model's ability to determine the number of closing brackets. Bracket number determination is based on the nesting depth within the code. The process involves systematically removing internal parts of a model. This removal continues until the model's performance noticeably decreases. The goal is to pinpoint the smallest internal mechanism essential for task completion. This identifies the core components driving the model's functionality. Optimization focuses on refining these critical mechanisms. This approach enhances efficiency by eliminating unnecessary elements. The quote closing circuit is designed to automatically manage quotation marks in text. The circuit's design emphasizes compactness, utilizing only a few essential units and connections. One unit within the circuit is dedicated to detecting the presence of quotation marks. Another specialized unit distinguishes between single and double quotation marks for accurate processing. A signal is transmitted to indicate the appropriate closing quote type. This signal propagates through the system to the end of the sequence. The signal ensures the correct quote type is used for closure. This process illustrates a traceable internal routine within the system. The bracket counting task involves identifying opening brackets within a given input. Detectors are employed to specifically locate and recognize these opening brackets. Each detected opening bracket generates a signal. These signals are then aggregated by a dedicated component within the circuit. The aggregation process determines the level of nesting based on the number of detected brackets. The final output reflects the depth of bracket nesting in the input. The model assesses the nesting depth of elements within a structure. This assessment determines the number of closing brackets required. The system employs a tangible internal counting mechanism. This mechanism tracks the level of nesting. Based on the count, the model decides whether one or two closing brackets are necessary. This demonstrates a traceable and logical process for bracket placement. When a variable is created, the system assigns a type. This type is stored as a marker associated with the variable. The marker indicates the data type of the variable. This marker is later retrieved when the variable is accessed. The retrieved marker ensures the correct operation is applied for modification. The model possesses the ability to store information. The model can also retrieve stored information. This demonstrates a form of memory within the model. The memory function is characterized by precision. It is not a vague or general storage mechanism. Instead, it operates as a precise internal process. Bridges serve as a mechanism for translating information between different types of models. Specifically, they facilitate the flow of information between sparse and dense models. This translation process enables the transfer of interpretable features. Interpretable features are characteristics or attributes that are easily understood and explained. The ultimate goal is to apply these interpretable features to real-world applications. Feature mapping involves manipulating internal signals within a sparse model. These manipulated signals are then injected into a dense model. This process allows for the observation of how interpretable features affect the behavior of complex systems. The injection of tweaked signals demonstrates the influence of specific features. This method provides insights into how individual features contribute to the overall system behavior. The approach shows how interpretable features can alter behavior in full-scale systems. OpenAI has released the Circuit Sparsity model. This model is built on the GPT-2 scale architecture. The Circuit Sparsity model is accessible on Hugging Face. A toolkit for the model is available on GitHub. Users are enabled to upload and interact with a specified model. The model can be executed using Python code for dynamic interaction. Users can explore the internal circuits and mechanisms of the model. The exploration reveals the essential components required for the model's operation. The current release signals a change in AI development strategy. The focus is shifting from solely enhancing AI capabilities to improving its transparency. The goal is to make AI's internal processes more understandable. This enhanced legibility enables a deeper understanding of how AI systems function. Understanding AI internal mechanics is becoming increasingly important. AI models are now responsible for generating code. AI is automating workflows across various industries. AI algorithms are filtering content, influencing information access. Circuit sparsity is an approach to enhance AI system attributes. It aims to improve control over AI system operations. Increased reliability is another key objective of circuit sparsity. Circuit sparsity seeks to make AI behavior more predictable. These improvements address critical industry demands for advanced AI. Readable AI provides the ability to audit and understand AI models. It also helps in reducing emergent behavior in AI systems. However, readable AI introduces potential risks. One risk is the possibility of manipulating models in unforeseen ways. This manipulation could lead to unintended and potentially harmful outcomes. The central question revolves around the impact of making internal behavior more transparent. One possibility is that increased legibility will lead to genuine oversight and accountability. Alternatively, it could accelerate capability development within the organization. Enhanced legibility might also amplify the organization's influence. The potential for accelerated capability and influence may be currently underestimated. Therefore, a careful evaluation of both oversight and capability impacts is crucial. Circuit sparsity is poised to significantly influence the field of artificial intelligence. Its development will likely reshape AI safety protocols and methodologies. The control mechanisms within AI systems could be fundamentally altered by circuit sparsity. The range of applications for AI is expected to expand and diversify due to this technology. These implications suggest a rapid evolution in the capabilities and governance of AI.